Thanks for the introduction and thanks for the opportunity to be here. It's been really wonderful to hear so much about Fred's life and work. I never had the opportunity to meet him, but now I feel like I have a bit of a sense for who he was. Now I have to say, computation is the way to the truth, but this isn't a terribly computational project. However, I think that there are some other tie-ins, non-mathematical tie-ins. For example, the question I'm going to be talking about is a very naive question, very classical question. And also the way that this project came about and everything I'm going to say is joint work with Aravind Ashok, Brian Shin, and Tariq Syed. Tariq was in Los Angeles as a postdoc for a year. Brian and I are both at University of California, Los Angeles. Aravind is at USC. And we all started meeting in Aravind's office and just sort of turning over pebbles on the beach, seeing what common ideas we all were interested in, what we could say about them. And eventually, this problem kind of came together. So hearing about how Fred collaborated and the way he did mathematics, it sort of, I realized, hey, that project is kind of an example of this discovery process. Okay, great. So the basic question that I want to address, let me fix some notation to start. So throughout, R will always be commutative and associative and unital, just ordinary ring. Let's say that it's also a K algebra where K for now is just any field, although we'll be a bit more specific later. And let's say that has dimension in the Zariski sense, D. M is going to be a finitely generated projective module over the ring R. And just to remind you, a projective module is a direct summand of a free module of some rank if it's finitely generated, i.e. there's a surjection from some free module. So the basic question that we can ask is what is the lowest rank free module that surjects onto M? In other words, how many elements M are needed or are necessary to generate M as an R module. Again, as I alluded to, this is a very classical question. And I really mean this in like the literal sense, no homotopy theory involved yet. Now, I should mention that this is, there are variants of this question. You could ask this question for modules that aren't finitely generated projective. You could ask this question for ideals, also very interesting, but I'm going to focus on the projective module case because that's the case that we can access via homotopy theoretic methods. Okay, so classical answers. So there is the famous Forster-Swan theorem, which was proved in some version by Forster in '64 and improved and sort of, well, modified to some extent by Swan in '67, which says the following: with hypotheses as above, M can be generated by R plus D elements. D is the Zariski dimension of the base ring, and R is the rank of your projective module. Now, I should mention, I would be... if you like, it's the local rank. If you look at, you can produce for any, so we have a ring R, we can localize the module M. Well, this might not be the most direct way to define it, but it's a way. We can localize it in any prime ideal, and then we can look at the quotient by P, MP. This is a module over the field R localized. So it's a module over R localized at P mod P, R localized at P. This is a module over a field that has some rank, and that's going to be a constant for, at least for a finitely generated projective module over a domain. Maybe let me add that. So you can say things for things that aren't domains, but like, let's not. We want something that's connected. So the dimension over, well, I guess this is what you might call K of P of this is the rank. Right. Now, another way to think about it, maybe this would have been the more glib answer that will get at how we're going to think about things going forward. Finally generated projective modules by Sayre correspond to vector bundles, algebraic vector bundles, and those have rank in the sense that you're used to as a topologist, algebraic vector bundles. But yeah. And I'm probably close to my limit here. So I should also mention that the Forster-Swan theorem applies more generally. You don't have to have a projective module. You don't have to be working over a field, but the formula is a lot more complicated. So this is the strongest result you can deduce for projective modules from their work. Sure, you're right. There's no reason to do it this way. Great. Sure, go ahead.
From your definition of rank, is it easy to see that it doesn't depend on the prime P that you choose?
So I guess I think it's maybe it's not. You have to think about some commutative algebra, which isn't what I want to do. Certainly, if you take the supremum of overall P, you'll get the right notion of rank. I believe you should always. Yeah, sorry, I'm not immediately seeing commutative algebra, but I think it's not so hard to see. Maybe like a Nakayama lemma thing or something. But if you take the geometric definition, maybe that's more satisfying for this audience anyway. Thanks. Yeah. So then the next sort of result along these lines is due to Murty in 94, where he proves the following. So M can be R plus D minus 1 generated, meaning that there is a surjection from the free module R to the R plus D minus 1, if and only if the Dietz-Segre class of M is equal to 0 in the Dietz-Chow group of X, where here I'm going to throw out by X for spec of R. Important, here K has to be algebraically closed. So R is an algebra over an algebraically closed field. So this should have been a hypothesis at the beginning. This should go in here, right? So what is the Segre class? Well, we know that M direct sum N is R to the R plus D for some projective module N of rank D by the Forster-Swan theorem. It's the kernel of that surjection that you have. And the Segre class is by definition, the total Segre class is just the total Chern class of this stable inverse, which doesn't depend on the choice of stable inverse. But we can see that it has a potentially non-zero Dietz-graded piece because it's a rank D module. And the condition, so SD of M is just CD of N, and this condition corresponds to splitting a trivial, or it's the sort of first obstruction to splitting a trivial bundle from a rank D complementary bundle. So you can see that this would be a necessary condition, but in fact is also a sufficient condition, and that's Murty's theorem for K algebraically closed. So what I want to do in this talk is improve upon both of these results in 3 different ways. So first of all, we'll prove results that depend only on something that I'll sometimes refer to as the homotopy dimension. I've been trying to eliminate this language, but what I mean by that is the Nisnevich homological dimension of spec of R. So this is a smooth affine variety. X is a smooth affine variety. We can look at sheaves on the small Nisnevich site. That's some étale topology on schemes over X. X equals spec of R. And the Nisnevich cohomological dimension is the maximum D such that cohomology with coefficients in Nisnevich sheaves can be non-zero. Right, so this is some cohomological dimension. If I put Zariski there instead of Nisnevich, it would just be the maximum D such that HD of X with coefficients in a Zariski sheaf is non-zero. And note, this homotopy dimension is less than or equal to the usual dimension, the dimension as a variety. So, for example, if we take a smooth affine variety of dimension D and we look at a vector bundle over it, that turns out to be have the same homotopy dimension as the base. Therefore, we actually do get a number of sort of additional examples where these two theorems will apply when we replace dimension by homotopy dimension. So that's this. Oops, sorry, I don't know why I wrote D. So this first improvement is just going to be sort of a formal consequence of the theory that we use. The next two ways that I want to sort of improve or modify these classical theorems are a bit less formal. So first of all, we want to improve Murty's theorem for K not necessarily algebraically closed. And Murty's theorem, it will, when I say that we'll prove a version for K not algebraically closed, it's not going to just be the Segre class anymore. The sort of necessary and sufficient condition to be R plus D minus 1 generated is going to involve a little bit more, but we will get sort of a result that matches up nicely. And the third way that we want to sort of pursue generalizations is to look at R plus D minus 2 generation. With some hypotheses on the field. There are many different things you can try to say, but it gets a bit messy. If you're familiar with obstruction theory, Murty's result is like a first obstruction problem. This is a second obstruction problem, which sort of depends on some choices at the first stage. It's a bit hard to say something really concrete, but we can say some things. Okay, so what I want to do next, maybe I'll put them on this board because I want to ideally keep them up for the whole talk, is just state 3 theorems that we can prove. And then I'll set up some theory and talk about the proofs, which are pretty simple once you draw the correct diagrams. Okay, so throughout what I'm going to say next, X is going to be spec of a ring. It's going to be a smooth affine K scheme for K a perfect field. And this is just a technical hypothesis that we need certain tools that we need for certain tools for motivic homotopy theory to work. And the homotopy dimension, the Nisnevich cohomological dimension of X, going to be equal to something called D. So previously D was the actual dimension, and I'm just replacing it with this slightly more lenient notion of dimension. M is going to be a finitely generated projective module, as before, of rank R over the ring R. So it's a finitely generated projective R module. And the theorems that we can prove, these are our standing hypotheses for the theorems following. So theorem 1 is the homotopy Forster-Swan theorem. So this is Ashok, myself, Shin, Syed. And this says that M can be R plus D. Where here D is potentially less than the Zariski dimension of the space. So this is addressing item 1 in the ways that I'd like to improve these results. We just literally replace the genuine algebraic geometric dimension with the Nisnevich cohomological dimension. So theorem 2 is our version of Murty's theorem. It's by the same authors, of course. So this says if D is even, the Nisnevich cohomological dimension of X is even, then M can be R plus D minus 1 generated. So there exists a surjection to M from a rank R plus D minus 1 free R module, if and only if the dth Segre class of M is equal to 0 in the dth Chow group of X. So maybe I should have mentioned this before. Chow upper D, that's codimension D cycles modulo rational equivalence. So these are like points. It's the Chow group of 0 cycles on X. Now, if D is odd, so in the case that D is even, we get Murty's theorem essentially with only very mild hypotheses that our field is perfect. There's tons of perfect fields out there. The field does not have to be algebraically closed. But if D is odd, we do have a slightly more technical condition. So the same conclusion holds, or the condition of R plus D minus 1 generation is equivalent to a slightly more annoying condition. So if and only if for n a rank D stable inverse for M. So by the Hammett-Jacobi-Forster-Swan theorem, there exists a module n of rank D, so that M direct sum n is free of rank R plus D. So we choose any such module, and the condition is that the dth Euler class of this module n is equal to 0 in now the dth Chow-Witt group. So let me say just a little bit about what this means. Yes.
Okay, my question
yes,
was.
I think so. Oh, yeah. So the question was, does theorem 1 imply the Suslin-Serre theorem about, that's the one about cancellation of modules? So sorry, I'm sort of, I think yes, but I'd have to like write it down to make sure all the ranks and dimensions match up. So that's the one that says modules of a certain rank are cancelable, right? Oh, they're all free. Yes, yes. Modules over polynomial rings are all free. Exactly. So yeah, so I think this implies that if you have, well, okay, I'm not exactly sure. I think it also, to say that it implies it, I'd be a little bit concerned because I feel like a lot of background results might implicitly use this in A1 homotopy theory. But yeah, so I guess you're saying if you have a polynomial algebra, that's of homotopy dimension 0. Yes, exactly. It's of homotopy dimension 0 because it's an affine variety. So therefore, this tells you that there's a surjection from a free rank R module. And it's a rank R projective module, so that must be an isomorphism. So yeah, it does. But again, I'm a little bit concerned that some of the theorems we use might implicitly use the Suslin-Serre theorem. So maybe take implies as more of a like observation than a theorem. Great. So was there another question or? All set, all set. No. I think I just saw you holding the microphone and I thought you were, it's all good. Right. So this Chow-Witt group, this is a Chow-Witt group. And this is some sort of a quadratic enrichment of Chow groups. There's a natural map from the dth Chow-Witt group to the dth Chow group, induced by some map involving Milnor K-theory versus Milnor-Witt K-theory, which I don't want to get into too much. And under this map, the Euler class of n, the dth Euler class of n, or in fact, all the dth Euler class of n maps to the dth Chern class of n, i.e. we exactly are getting that we have some lift of the condition that the dth Segre class of M vanishes. Now there's a more geometric way to think about this, which is that vanishing of the dth, or the Euler class of n is the same thing as, it's the first obstruction to splitting a trivial bundle from n. So really this is something, this is a geometric condition in some sense. So this is the first obstruction to splitting a trivial, well, I guess I'm talking about modules instead of saying bundle, let me say a trivial rank 1 module, i.e. a copy of R from N. There's an instruction theoretic way to think about it. It also might be useful just to think about it as a lift of the dth Turing class to this quadratic sort of version of Chow groups. Maybe a quick corollary of theorem 2. So under some hypotheses on the field K, the natural map from Chow to Chow-Witt becomes an isomorphism. And then we just recover Murphy's theorem for a large class of fields. So if K has 2 cohomological dimension, at most 1, then M is R plus D minus 1 generated if and only if the dth Segre class is equal to 0. And that's because this Euler class condition just reduces to a Turing class condition on the complement, which is exactly the Segre class, the dth graded piece. So 2 cohomological dimension, that has to do with if you look at the absolute Galois group of K, you can look at cohomology with coefficients in 2 torsion modules, and you're asking it to always vanish above degree 2, at degree 2 and above. But an example of such a field would be a finite field for P in odd prime. Okay, and now the last theorem I want to state, this one's a bit annoying. There are many different versions that I could try to state for you, so I'm just going to state a sort of simple one. It's by the same list of authors. Oh wait, I realize the dash usually is used, sometimes it's used to mean just the person speaking. So let me just say same to make sure there's no confusion. All 4 of us are on all of these results. So if we suppose that our perfect field K is additionally algebraically closed, then and also we have some annoying cohomological vanishing condition, which is that the dth Nisnevich cohomology of our scheme X, our smooth affine scheme X, with coefficients in some Nisnevich sheaf, which I'll write like this, maybe just you don't have to worry about what it is too much, is identically 0. This is some cohomology of X. Then M can be R plus D minus 2 generated if and only if the top 2 graded pieces of the Segre class are 0. And the first one is in the dth Chow group, the second is in the D minus first Chow group. Now, this proceeds via some analysis where you're doing some obstruction theory. It looks like classical obstruction theory, but everything involved is a sheaf instead of a group, et cetera, et cetera. And this ends up being an obstruction group you kind of can't get a handle on. But once you assume it's 0, you just get some Chow groups and you can identify the obstructions with Segre classes. So as a consequence of this, we get the following. If K is algebraically closed and of characteristic 0, then a recent in Ashok, Bachman, and Hopkins's recent paper on P1 stabilization in Motivic homotopy theory, they actually prove that under this hypothesis on the field, this group vanishes identically for any smooth, for like very generally. So at least for X, a smooth affine variety of dimension D. I think they need it to be smooth and affine, homotopy dimension D. So if K is algebraically closed, then the top 2 Segre classes are the only obstructions to R plus D minus 2 generation. I should mention you can also give a direct proof of this fact using Murty's co-rank 2 splitting conjecture and characteristic 0, which is actually what they use the vanishing result for this group to prove in the paper. So this is kind of closely related to already known major results. But most of these other theorems, we don't know of a direct argument that doesn't use some new things. Okay, great. So how am I doing for time? I think I'm doing okay, but I haven't, sorry?
15 minutes left, I guess.
Okay, great. So what I want to do next is briefly sketch sort of the background setup for these problems in order to set up the type of obstruction theory that I'll be doing.
Sorry, 25 minutes left. I miscalculated.
Oh, that's much better. Thank you. I was going to say 15 minutes. Very brief.
Sorry about that.
No worries. It's better than the other way. If you said 25 and then you said sorry 15, then I might pass out, just give up. As we know, computation is the way to the truth. So I'm glad you recomputed that number. Okay, so I think I'm just going to work on these two boards to avoid having to think about the cutoff point for this. So for the rest of the talk, I'll first give sort of a sketch of the theory, and then I'll prove these theorems. If I have time, I would love to see something about another result we prove, which is that we can prove symplectic versions of each of these theorems. So if you have a module with a symplectic structure, you can ask when is it a summand of a hyperbolic module, a hyperbolic symplectic module of a given rank, and it turns out the sort of motivic setup just spits out some results. We have a symplectic Forster-Swan theorem, for example, but I don't know if I'll have time to talk about that, so I just wanted to mention it now when I'm talking about the theorems, just in case. Okay, so the setting for this talk is the category of motivic spaces over our perfect field K. What do I mean by a motivic space? Well, this is a pre-sheaf on the category of smooth K schemes valued in spaces, which satisfies Nisnevich descent. So there's the Nisnevich topology, which sits between the Zariski and Natal topologies on smooth K schemes. So this satisfies Nisnevich descent. So it's a sheaf for some topology. Never spell descent correctly. Is that decent or descent, or are they spelled? I don't know. It satisfies the thing that makes sense in this case. And it's A1 local. So if I have U a smooth K scheme, I can look at the natural map from U times A1 to U given by projection. So this is A1 over K, but I'll suppress the K, given by projection onto the first factor. And this induces a map in the opposite direction when I apply my contravariant functor. And the A1 local condition simply says that this is an equivalence of topological spaces. Now, I'm thinking about this category as an infinity category so that I can say things that are literally true instead of having to say things that are true up to like fibrant and cofibrant replacement. But I'm not actually going to do anything infinity categorical in this talk. Everything that I say is going to be in the homotopy category of this infinity category. Now, a couple observations is that if we look at smooth K schemes, we can take the Oneida embedding into pre-sheaves, let's say pre-sheaves on smooth K schemes, and then we can localize to get a Nisnevich sheaf that's also A1 local, i.e. a motivic space. And via this composite, we can think about any smooth K scheme as a motivic space. I will generally conflate the smooth K scheme with its image in motivic spaces because it never actually causes any confusion. So for example, I'll talk about the Grassmannian of R planes in AN as a motivic space. And what I mean is that you view this as its functor of points, and then you localize it. Yeah, it never will really cause any confusion, but if I start writing down symbols for varieties that you know about, I'm viewing them as motivic spaces via this procedure. Also, if you have any topological space, let's call it X. Oh no, X is our spec of our ring. Let's call it Y. So then you get a constant presheaf, which you can, to that you can associate a motivic space. So I can view, if I have a topological space that I know about, I can view it as a motivic space via this sort of map that takes a topological space to the constant presheaf from the smooth K-schemes to top, and then I localize it motivically. Also, if I have a smooth K-scheme, I can view that as a motivic space. And sort of a warning here is that we have sort of these two separate geometric structures, the algebraic structure on the source category and the sort of topological structure on the target category of these sheaves. But as if you've seen like any motivic homotivy theory, you might know, motivic localization mixes these things. For example, the smooth K-scheme P1 ends up being equivalent in the category of motivic spaces to the motivic space associated to the topological space S1 smash with the motivic space associated to the smooth K-scheme GM, the multiplicative group. This smash, I should say something about that. We have various constructions from topology, which are inherited from the source category. So we have smash products, fibers, co-fibers. I'll just say ... And if I write a symbol that you're confused about, feel free to ask, but the most likely answer is that I mean it just comes from the fact that we're working with sheaves valued in topological spaces. Okay, so the main reason that this is a useful category for studying projective modules, which we know finally generated projective modules are the same as algebraic vector bundles, is the affine representability theorem. Proved in a somewhat constrained context by Morel, and then in full generality by Ashok, Oiwa, Went. I didn't write down the dates on these, but you can look at that. So, and this says the following: if we look at algebraic vector bundles on X, so X now should be, let me just emphasize this. So X is spec of R, it's a smooth affine K scheme for K field. You can do this for some things that are not fields, but let's just state it for fields. Then algebraic vector bundles of rank R on X up to isomorphism of algebraic vector bundles. So this is the isomorphism classes of sort of vector bundles in the classical algebra geometric sense, locally free sheaves, projective modules, are naturally in bijection with A1 homotivy classes of maps from X into the infinite Grassmannian. So by this, I mean you take the colimit and motivic spaces of your finite Grassmannians over N. So Grassmannian of R planes in AN maps to Grassmannian of R planes in AN plus 1. And then you could take the colimit and motivic spaces because it's a sheaf category, so we have colimits. What do I mean by this? By definition, this is maps in the category of motivic spaces from X. So homotivy classes of maps are just maps in the homotivy category. I don't have to worry about things being fibrant or cofibrant because I've done things infinity categorically. Okay, so let's see. The next thing I want to talk about is the way to build maps. So to study projective modules, I want to build a map into the Grassmannian, but I don't just want to do that. I think now I'm sort of forced to use this board, but that's okay. I want to look at building maps and building factorizations of maps. So I have my infinite Grassmannian, which classifies vector bundles. And this receives a map from the Motivic space associated to the finite Grassmannian. Now, a vector bundle corresponds to a map from X into here. I'm going to write M for my module, my rank R module that over spec of R that I start with. And this space classifies A1 homotopy classes of maps into the Grassmannian, classifies vector bundles together with a surjection from a rank R module. That's even true at the level of functors of points for the scheme Grassmannian of R planes in AN. So what I'm really looking for, if I want to ask if X can be R plus D generated, I take N equals R plus D in this diagram, and I try to build a lift here. So now if you're sort of familiar, so I'm asking for what N does such a lift exist for my given module M. Now, if you're familiar with classical homotopy theory, this is like the setup for Moore-Postnikov theory. You have a map to a given space and you want to lift it to another, and you can do this in stages. So the setup for Motivic Moore-Postnikov theory basically looks exactly like the classical one, but you just have to be a bit careful about what your obstruction groups are at each stage. So in the interest of time, let me just write something down. So in general, you have E going to be in Motivic spaces, and the fiber, the homotopy fiber, which exists because we can take fibers in this category, it should satisfy the property that pi 1, A1 of F is equal to 0. Another thing we have are homotopy sheaves. I should have said that. Right, so maybe I'll just say this in words. We have various constructions like smash products and fibers. We also can just take a sheaf, a map from smooth case schemes op to top, satisfying these conditions, and post-compose with homotopy groups. Now we have to Nisnavitch sheafify, but this gives us some homotopy sheaf as opposed to homotopy group. It's a Nisnavitch sheaf, so we can take cohomology with respect to that sheaf, et cetera, et cetera. So the condition is that the first homotopy sheaf of the fiber is 0. So now the Motivic Moore-Postnikov theory tells us that we can build a tower starting with B, going to a Motivic Eilenberg-MacLane space. So I also want that the 0th. So actually, I think in the interest of time, I'm going to do sort of the oriented version of the problem. So instead of looking at just, so I could look at generation of oriented modules. So I'll just put SL up here. You can construct oriented Grassmannians and oriented classifying spaces. And this is going to allow me to simplify things somewhat. So let's assume instead that pi 1 of B is equal to pi 1. This is the A1 homotopy sheaf of E is equal to pi 0 of B, 0 of E. These are all trivial as groups or sheaves of groups or sheaves of sets. That's just going to sort of allow me to avoid having to talk about twists in my Postnikov towers, my Moore-Postnikov towers, which you can do, but it's a little bit annoying to have to write it down. So you have a map from B to K pi I of the fiber, I plus 1. There's homotopy fiber here I'm going to call E I plus 1. And E maps to each of these. And the facts are that to lift, or I guess I should have written at least 2 of these guys. So let's call this EI, off by 1. This is EI minus 1, and this maps to B. So you have this tower of fibrations over your base B interpolating to F. And as in classical homotopy theory, given a map, which we'll call F I minus 1 from our Motivic space X, which is spec of R, to E I minus 1. A lift to EI exists. So this is some Motivic Eilenberg McLean space if and only if some class corresponding to this, the composite of this map with your given map Fi, so let's call this Ki, so if and only if the class K sub I composed with Fi minus 1 is equal to 0 in the Motivic cohomology group each I plus 1 Motivic of X with cohomology in pi I F. We have some class that needs to be 0. The choices of a lift are a torser for some quotient of another cohomology group, but that's not going to matter for this problem, so I won't write it down. And the other relevant fact, I know I'm close to the end of my time and where I need to write this, is that homotopy classes of maps from X to E are naturally in bijection with homotopy classes of maps from X to the deep stage in this tower, where D is the Misnevich cohomological dimension of X. So in the last, I think I have 4 minutes left. Is that correct?
I would say it's closer to 10 minutes left, but 4 minutes, you can have more time for questions too if you want.
Okay, well, maybe I should have done the not oriented version. Basically, you can add in an action of the fundamental group of the base space on everything in this tower, and you end up with an obstruction theory where you're looking at Misnevich cohomology with twisted coefficients for your obstruction groups, as long as E and B or A1 simply connected. So just you have the hypothesis that pi 0 is trivial. And the map from E to B induces an isomorphism on pi 1, then you still get this Motivic Moore-Postnikov theory. And a great reference for the twisted version is a paper by Aravind Ashok and Jean Fassel. I believe it was published in 2015. It's called Splitting Vector Bundles Outside the Stable Range. But if you look up this data and splitting vector bundles, you will find it. This is, I think, the only reference I found that has a really clear exposition of the twisted version of Moore-Postnikov theory, which is actually what we use in this paper. But I've committed to doing the oriented version, so I'll continue with this. Maybe I should swap these. So basically what I need to do is apply this theory to E equals Grassmannian of oriented planes in AN, oriented R planes in AN, and B is equal to the infinite Grassmannian. So in order to do this, I need to identify the homotopy fiber of my map. So this is, I guess, section 2, which is the proof section. Section 0 was everything I said before I had section numbers. Proofs. And again, I'll just say oriented versions, but you can add in twists everywhere and make the theorems that I wrote over there true. Sorry, I realized there's a small error in this theorem. It's still a Chow-Witt group, but you have to twist by a line bundle. It still maps here. You still have a twisted Euler class, but L is going to be the determinant bundle of Xi, where Xi is the vector bundle associated to this projective module M. So there is, I forgot to mention the twisting issue when I stated the theorem. Just something that kind of comes along for the ride. Okay, so the oriented version proof that I want to give, I first need to state a lemma for you. So there is an A1 fiber sequence from starting with the oriented Grassmannian, going to the infinite oriented Grassmannian. And the fiber here is going to be GL sorry, it should be SL, n mod SL n minus R. So this tells us that to apply Moore-Postnikov theory to lifting a vector bundle and map to here, an oriented vector bundle, to an oriented vector bundle together with a choice of surjection, we need to understand the homotopy sheaves of this variety. So our second lemma computes the first couple homotopy sheaves of this, this motivic space. Sorry, I said variety, but it's a quotient, so maybe it's a motivic space. I guess in this case, you can also think about it as a variety. So the motivic homotopy sheaves in this case, and I guess I might also mention that this quotient is actually a Stiefel variety, can be identified as follows. So the homotopy sheaves are 0 if I is strictly less than n minus r. We get the n minus r plus first Milnor K-theory sheaf if I is equal to n minus r and n minus r is odd. And we get the n minus r plus first Milnor-Witt K-theory sheaf if I is equal to n minus r and n minus r is even. So Milnor-Witt corresponds to Chow-Witt. Milnor corresponds to Chow. You can see that if you take n equals r plus c minus 1, you sort of get the right parity for theorem 2, but that's just to kind of make sure things are making sense so far. And then for the higher homotopy sheaves, we have some more complicated formulas proving that they fit into certain long exact sequences of sort of known sheaves. For example, these are known sheaves, though I won't define them for you. But we can say the thing that we actually need to prove our theorems is that there is, for I equals n minus r plus 1, there's always a surjection from a n minus r plus 1, remove 0. Oops, sorry, this should be pi n minus r plus 1 to our homotopy sheaf. So it's a quotient of some homotopy sheaf of a motivic sphere, a punctured affine space. And I don't think I'm going to get to it, but this surjection is sort of, it's where this vanishing condition comes from. Here, again, when you take, in that case, n equals r plus d minus 2. Okay, so now with everything in hand, I can actually prove the oriented version, at least, of theorem 1 for you. And I'll just sort of wave my hands and say, oh, actually, we proved theorem 1. For theorem 1, we see that if you take n equals r plus d, so we're looking at lifts along this map, all of the oriented, so all of the obstructions below dimension d, which is because of our Nisnevich-Kolmogorov dimension vanishing hypothesis, vanish. So n minus r is equal to d. All of the homotopy sheaves below dimension d vanish. So all obstruction groups used to build a map from x to the d Moore-Postnikov stage of this guy just are identically 0. They vanish identically. So for theorem 2 and 3, I'm not going to actually go through the proof, but I'm just going to draw a big diagram, which is sort of the key to the proof. So the diagram is the following. So we have the lifting problem that we care about, the Grassmannian of R planes, and I'll do this for general n because actually this diagram allows us to identify the first obstruction to n generation for any n, but then we're going to apply it for specific n to prove theorems 2 and 3 if we had time. So we have this map that we care about. I'll call this map A. It's the lifting problem we care about with fiber that we identified in the lemma. Then we also have another lifting problem, which is sort of the reduced generators by one lifting problem. So suppose that we had a map to the Grassmannian of oriented R-planes in AN plus 1. Well, we could just ask, okay, can we reduce the number of generators by 1? This is a quality, and this, of course, receives a map to the colimits at oriented Grassmannian of planes in infinite space. And the fiber here turns out to be AN minus R subtract 0 times loops on AN plus 1 minus 0. So this is some motivic spheres and loops on a motivic sphere, and we have a projection map here that I'll call G. Now I can also project off. So supposing I have a surjection from a free module of a oriented free module of rank n, I can look at the associated the kernel of that surjection. This gives me a rank n minus r module, a rank n minus r plus 1 module. The fiber of this map is also something that we can identify. It's just AN minus R subtract 0. So I'm going to call this map D and this map C. So the idea of the proof is that we compare the primary obstructions to the lifting problems for lifting along A, B, and C. So first of all, the first obstruction to this lifting problem is precisely the Euler class, essentially by the definition I've given you for the Euler class. It's something, the primary obstruction to this lifting problem takes values in it's a motivic cohomology group with coefficients in pi n minus r of or pi n minus r minus 1 of an minus r subtract 0, which is a Milnor-Witt K-theory sheaf. And in the dimension that it occurs, it's precisely a Chow-Witt group. So this is just the Euler class. So we find that actually, for R at least 2, the primary, the first obstruction to this lifting problem is also the Euler class. This doesn't contribute, and you just get an isomorphism on the first obstruction groups. So then the question is really, what does the obstruction for lifting along B map to when you apply this map G on homotopy? So this is same for B. And then what we find is that the obstruction group is either mapped onto isomorphically by G for A, in which case the Euler class is still the obstruction, or we get a quotient, which is precisely the map from Chow-Witt D to Chow D, and that's the case where we get the Segre class. So lifting along A, we study the map G on homotopy, and identify both the obstruction group and the obstruction class. I'll just say obstructions. We identify the image of the obstruction with either an Euler class or a Segre class, depending on the parity. And I'll stop there.